It's my great pleasure to introduce Roman Walch, and he will be talking about Monolith, which is a new ZK-friendly hash function, right? Take it away.
Hi, yeah, so macro seems to work. So this work is a joint work with some other researchers like Lorenzo Grassi, Dimitri, who was speaking in this room in the 2 hours ago, with Reinhard Lüftenegger, Christian Rechberger, Markus Stoffnegger is also here, and me, of course, Roman Walch. So we had 2 talks already about symmetric hash functions for zero knowledge. So I hope by now I don't need to convince you that they are important for zero knowledge use cases, but some examples I still want to mention here. So basically, whenever you have some Merkle trees in some zero knowledge use cases, you also need a symmetric hash function. When you have a Merkle tree, you can then also build directly some use cases like anonymous transactions, anonymous credentials. Hash functions are also used in ZK rollups, where you basically outsource a lot of computation on some side chains, and on the main chain, you're basically just verifying that in a zero knowledge proof that everything you did on the side chain was done correctly. And also for recursive snarks, which is also a hot topic in zero knowledge, there we also use some symmetric hash functions. And symmetric cryptographers have been busy in the last years and have come up with new symmetric hash functions which are actually optimized for these types of use cases. So most notably we have the Poseidon hash function, which is nowadays implemented in many different zero knowledge proof systems, but there are plenty more of these functions like Rescue, Griffin, Anemoy, and many more. So the state of the art right now is that for performance, these new hash functions are significantly faster than traditional hash functions like SHA-3 inside of a zero knowledge proof system. But when we consider the performance outside of the proof system, so just for hashing some data, these functions are still significantly slower compared to SHA-2, SHA-3, and these traditional hash functions. However, as we have seen in some recent use cases, plain hashing performance actually also matters for zero knowledge use cases. For example, in recursive proof systems, and I have been had people talking about a concrete use case for recursive proof systems, namely a signature aggregation. In these use cases, actually a proofer during every recursion step has to build a Merkle tree, hashing a lot of data, and then show inside of a zero knowledge proof that the correct data has been hashed, basically. And here, plain performance actually matters in building these Merkle trees. And in some concrete use cases, which we have found in some papers, people have shown that using Poseidon or similar hash functions, up to half of whole proof generation is actually due to hashing and building these Merkle trees. So in these use cases, plain performance still matters a lot. So when we consider this, what the ideal hash function would actually be, it would be a hash function that is super fast outside the zero knowledge proof, so just for hashing, but also be very efficient inside the zero knowledge proof. And that is, with these hash functions we have mentioned before, unfortunately not given. But luckily, in the last years, researchers in zero knowledge have come up with different kinds of lookup arguments, and this also gives researchers in symmetric cryptography a new angle to optimize for better symmetric hash functions. But if you think about it, when we have some large prime fields, for example, up to 256 bits, and your hash function is defined over these large prime fields, is actually not straightforward on how to build a lookup-based system for these hash functions. So you cannot really build a lookup table with 256 bits. That's unfortunately not possible. So researchers thought about that a lot and came up with some new designs which actually optimized for lookup tables. So here on the slides you can see that the first hash function using lookup tables, it is basically for the same team of researchers as for our new hash function here, and it's called reinforced concrete, and I've put the whole function here on the right side. And as I said, it's the first hash function actually making use of lookup arguments for better proof and plain performance. So it's built from 3 different kinds of layers, so we called them concrete, bricks, and bars. And so for the concrete layer, it's basically just matrix vector multiplication plus round constants, something that has been done in pretty much every hash function before. Also in the bricks layer, it's a standard nonlinear layer, also very similar to what has been done before. But the main novelty comes from this bars layer that we have here once in the middle of the permutation here. And here is where the lookup magic actually happens. So what we came up with in this design is that when we have a large field element up to 256 bits, we actually split it up into smaller field elements. So small in the area of about 10 bits. So on these smaller field elements, you can actually apply a lookup table. And after we have applied the lookup table, we can compose the results back to a large field element again. And so with this trick, we basically are able to use lookup tables inside of hash functions and get the better performance in plain and inside of proof systems. And you can also see here, this parse function is actually only applied once in the whole permutation. And that is since the actually switching from a large to a smaller field actually gives the hash functions a lot of security. So that is very good. So as a result, we were able to show that with this hash function, we are significantly faster for hashing outside the zero knowledge circuit than any previous hash function like Poseidon, Rescue, etc., etc. But we are still orders of magnitude slower than SHA-3, for example. And besides that, this reinforced concrete design has some different problem as well. So when we would say we want to build a similar hash function for smaller prime fields like Goldilocks prime field, which is used in some modern proof systems, then we cannot really apply this design strategy of reinforced concrete as is. Since the design that we had on the previous slide is not really flexible, it's fixed for a fixed state size of just 3 field elements, and that basically disqualifies it for smaller prime fields already, because the hash function itself would be insecure just from the field sizes. And so reinforced concrete can basically just be used for large prime fields, for example, for KCG-based proof systems or Fry-based proof systems, which are instantiated with large prime fields. Also, the decomposition in reinforced concrete is, so when getting from a larger field element to multiple smaller field elements, that is also kind of slow, and it is also difficult to generalize. So it's not really a problem for reinforced concrete, because we have seen parse is only applied once in the whole hash function, and we have 3 field elements. So we do not really decompose a lot of times. But when we go to a smaller field, we have to apply parse more often, and then this tedious and slow decomposition actually can become a bottleneck again. And a different problem is that when we implement reinforced concrete for just hashing, we kind of have to rely on lookup tables for getting better plane performance. And that is since the function that we evaluate with this lookup table is actually very slow. And so we kind of need this lookup table for fast plane performance. But as we know since the beginning of AES, when we have some lookup tables in hash functions, these may be susceptible to some cache-based side channel attacks. So when side channel attacks come to zero knowledge, this might actually be a problem in the future. But right now, I'm not really aware that this is exploited so far. But in the future, we might want to protect against side channels as well. So when we started this project, so basically what we wanted to achieve is a new hash function that is super fast in plain, also very fast inside of a zero knowledge proof system, and we wanted to achieve the performance in a zero knowledge proof system using the lookup arguments, similar to reinforced concrete, but we didn't want to rely on lookup arguments for the plain performance, such that the hash function can actually be implemented in a constant time implementation without much performance loss. And we were focusing on smaller prime fields. So here the Goldilocks prime field is used, for example, in Plonky 2, and also on the 31-bit prime field that is used in Plonky 3. And the design that we came up with, we dubbed Monolith. And now I'll talk a little bit about the design itself, and then I will talk about some benchmarks to show you the performance that we achieve. So here you can see one round of the monolith permutations. So we also, similar to reinforced concrete, have 3 different round functions. And we kept the same name. So we also have a parse function with decomposition and lookup tables. We have a nonlinear layer called bricks, and we have a linear layer called concrete. And now let's go a little bit into the details of these 3 different round functions. So the nonlinear layer we call bricks. So you can see here it is actually very simple. So on the first state element, we basically do nothing. And starting from the second state element, we just add the squaring of the previous element to the state word. And we do this since this has several different advantages. On one hand, it is very simple, requires just one addition and one multiplication per field element, so it will be very fast in plane. And also, since we only have one multiplication, so it's just a degree 2 polynomial that we evaluate here, it will also be very efficient inside of a zero-knowledge circuit. And finally, the squaring function actually gives you very good statistical properties, so this is good for the security of the hash function itself. Regarding the concrete layer, what we usually have here is a matrix vector multiplication plus some round constant C. But when you get to a smaller prime field, you actually need to have large state sizes. So the minimum state size we have with this hash function is actually 8 field elements. And having a generic matrix vector multiplication with for 8 field element state is usually very, very slow, and it can easily become the slowest part of the hash functions. So we need to use something here that is actually very fast to implement, but it also provides good security for the hash function. And what we decided to use here is using circular MDS matrices. So this was also done before. This is not an innovation from us. And basically, this MDS property is a property of the matrix that we need for the security of the hash function. And the circular property, so you can see it here, each row in the matrix is a rotation from the previous row. And when we have a matrix like that, we can actually use FFT to compute the matrix vector multiplication. So this will also be very fast in plane. And as I said, since it's an MDS matrix, it also has very good statistical properties. And together with the bricks layer from the previous slides, it will give our design good properties against statistical attacks. So finally, where the most important innovation from our design comes from is actually the parse function. So similar to reinforced concrete, we will follow decompose S-box compose design principle, but the decomposition is actually completely different to what we do in reinforced concrete. So instead of going from a large field element to multiple smaller field elements, we actually decompose the large field element into a bunch of 8-bit limbs. So, and then we do not apply some arithmetic function, but actually a binary function on these 8-bit limbs, on these decomposed limbs. And the function that we apply here just uses XOR gates, AND gates, and rotations. So this is something that is very, very fast when we implement it in plane. And furthermore, this S-box that we use here is chosen in a way that we can actually compute it on the whole field element without computing the decomposition first. So this thing is actually very, very fast in plane and does not require the use of a lookup table for fast hashing performance. But also, we similar to in reinforced concrete, switching from a large field to, in this case, bits, actually is very good for the security of the hash function. So also a small number of parse layers actually is enough for giving good algebraic security here. And for in the proof system, since usually it's not good doing some binary operations in the proof systems, but we can deal with that by using some lookup tables. So now I've talked about how the design actually looks. Now let's talk about performance, the performance that we can achieve with this design. And I will specifically focus here on the 64-bit Goldilocks prime field that is used, for example, in Plonky 2. So first, the modes of operations that we are going to use this permutation in. So on the bottom here, you have the general purpose hashing. So for general purpose hashing, you use the sponge mode of operation. So we've heard this in the 2 talks in the first session already. But when we actually have some use cases where, like in Merkle trees, where you have fixed sized inputs, you can actually go with a compression mode, which allows to be instantiated with a smaller state size, and therefore it will be faster. So in the benchmarks, in the next slides, we will always distinguish between the compression mode and the sponge mode. So and these are the 2 use cases for that. So about plain hashing performance on our system, when we instantiate Monolith with the compression mode, you can actually see that we get a compression after 130 nanoseconds. In the sponge mode, we get a runtime of 210 nanoseconds. When we compare this to, for example, SHA-3, then you can see that the compression mode is actually faster compared to SHA-3, and when we have the sponge mode, then we are slightly slower compared to SHA-3. Comparing Monolith to different ZK-friendly hash functions like Poseidon and its recent update Poseidon 2 that was presented at the previous ZK summit. You can see, so these are also instantiated with the Goldilocks prime field here. You can see that Monolith is significantly outperforms those two hash functions here. It's at least a factor of 5, but it goes easily up to a factor of 10 and 15. And here we also have benchmarks against DIP5 and DIP4 prime. These are basically the most important competitors to our hash functions, since they basically try to achieve the same, also with lookup tables. And you can also see here that Monolith outperforms both of them. Here on the, you see it here on the slides here. Regarding constant time performance, so since we have this special function in our bus layer that doesn't really require a lookup table for implementation, you can see that going from not constant time implementation to a constant time implementation has a very negligible overhead, and that comes from switching actually the field implementation to a constant time field implementation. That is also true for Poseidon and Poseidon 2, since they don't have any fancy lookup tables in there. But when we compare this to, for example, reinforced concrete, where the lookup table itself does not have a very nice structure to be implemented without the lookup arguments, the constant time performance would be significantly too slow. So regarding proof system performance, I first want to talk about how we actually arithmetize Monolith for a Plonkish proof system, and I will focus here on bars, since the bricks and concrete layer are basically straightforward. So to reminder, we have a decomposition and a binary S-box in here. So for the decomposition, we basically, for every field element that we want to decompose, we get 8 new witness variables, and also from the output of the lookup tables, we also have 8 new witness variables, and we basically have to add these two decomposition constraints to show that the decomposition was done correctly. And then we have to connect the input and the output via a lookup table, and this lookup table also includes already range checks for these limbs here. But so far it's basically straightforward, nothing magic here. But there's also one thing that we need to consider when we decompose field elements into smaller limbs, and that is basically that we have to ensure that these limbs together do not represent an element that is larger than our field size. This would give the prover actually an opportunity to cheat in some cases. So, and for this Goldilocks prime field, we actually can do this very cheaply, since this prime field has a very nice structure. You can see here in this hex representation of the maximum value in this prime field, it's actually a lot of ones here in the upper limbs and a lot of zeros here in the lower limbs. And that basically tells us whenever we have zeros here, the only thing, whenever we have non-zeros here, we do not allow here all 0xFF, because then the field element would, the decomposition would represent something that is not part of the field and would allow us to cheat. And in this proof system, we can actually do this by adding 2 constraints and 2 new witness variables. So these constraints actually enforce when these are not 0, we cannot have all ones here. So, and we only have to do this for the input, since the S-box that we have chosen in here, that ensures that every valid input always creates a valid output. All right, so this was how we arithmeticize Monolith, and now let's talk a little bit about actually the proof system performance. So here on the slides, I compare Monolith against DIP5, DIP4 prime, and also Poseidon and Poseidon 2. And what you can see here in the first column is that Monolith requires a little bit more lookup tables compared to DIP5 and DIP4 prime. And obviously Poseidon and Poseidon 2 do not require lookup tables here. Having more lookup tables, so we have seen this in the previous slides, lookup tables lead to more witness variables, so you can also see that Monolith requires a little bit more witness variable compared to the competitors. But the main advantage of Monolith actually is that the round function has a very low degree. This also affects prover performance. So our bricks function has only degree 2, whereas DIP5, DIP4 prime, and Poseidon, in this field, they require a round function of degree 7. So when we estimate prover performance by the area degree product, which basically witness times degree, you would see that we would estimate that Monolith actually leads to allows a performant prover compared to the other hash functions. So on the next slide, so we actually implemented a custom gate of Monolith inside the Plonky-2 proof system. More concretely, we are using a pull request on this proof system, which implements the lookup tables. And here, so we wanted to verify the estimated performance that we have. And so, this proof system actually comes with a Poseidon custom gate, which basically implements the whole Poseidon permutation in one row, whole custom gate. So we added Monolith here with the same parameters as the Poseidon hash function that already exists. So we actually added a custom gate for Monolith, which also just uses one row in the trace and compared the performance. So, and what we see here is that when we prove actually the Monolith permutation, we get a significantly faster prover compared to Poseidon, and also verification time is significantly faster, nearly a factor 2 for both. But since we are implementing the whole permutation in just one row, and we have seen on the previous slides we have significantly more witnesses, the result leads to a larger proof. But especially when we copy the plain runtime for these parameters from the slides before, where we have hashing time for Monolith in this setting with just 210 nanoseconds compared to Poseidon with more than 3000 nanoseconds, it's a factor of 15 here as a difference. We will say, especially with the combination of the faster prover and verifier, that Monolith significantly outperforms Poseidon in this setting here. And this plain performance obviously also carries over when we want to create a Merkle tree. So building a Merkle tree with Monolith is 15 times faster than building a Merkle tree with Poseidon here. So that basically were all the benchmarks. Now I want to conclude my talk. So the goal here was to implement, design a new hash function that is fast in plain, that is fast inside the zero knowledge circuit. And we came up with Monolith that is in plain nearly as fast as SHA-3, and it also outperforms Poseidon inside of the Plonky-2 proof system. Also, we designed Monolith such that it is easy to implement in a constant time, so it does not is not susceptible to cache-based side channel attacks. Our design is built using two different nonlinear layers. So in the bricks layer, it's a standard nonlinear layer like used in many other hash functions. And in the bars layer, we actually decompose for the first time into bits. And that gives us a lot of advantages in plain performance. So it's, as I said, currently the fastest zero-knowledge-friendly hash function for just plain hashing. And in our paper, we actually have a more generalized description. So we're not only focusing on the Goldilocks prime field, but on the Mersenne prime field as well. And similar primes can also be instantiated with our new hash function. So here are some links. So here on top we have the paper. It's on ePrint. So here are all the implementations where we benchmark the plain performance, and the Plonky-2 benchmarks that I had on the last slides can be found here on GitHub. So thank you all for your attention. It was my talk. If you have questions, please don't hesitate to ask.
Thanks a lot. So I guess we have time for one or two short questions. Let's start here.
So my question is, why do you need to extend to degree 7 in order to implement Poseidon? In Plonkish, you can definitely implement it with degree 3, maybe even less.
Yes, so in Poseidon, the nonlinear layer is the power map x to the power of t, and for this proof system, the smallest d you can use is 7. So, and when you directly use it here, you have degree 7, of course, but you can, of course, use a smaller degree round function, but that comes at the cost of larger witness sizes. Yeah, so having a smaller degree round function actually allows for more trade-offs.
Following that line, how easy will be to plug this into a transcript and then prove the correctness of the transcript into another proof? If you mean to do your recursion or something like that, have you explored that and whether it's?
Yeah, so it's the hash function itself is a permutation like Poseidon. So if there is implementation already there from Poseidon, you can just switch the permutation and then it should work like before. Yeah.
Hi, thanks for the talk. It seems that you were mostly targeting smaller fields, and
yes.
So have you thought about what would be the effect of applying monoliths on larger fields, but potentially using lasso?
Yeah, we have seen lasso, yes. Not sure yet what the cost metric in lasso would be, so we need. It's one of the things I wanted to talk with the designers. So I'm not sure how good Monolith would be there. Maybe some of my co-authors could answer the question. I don't know yet. But for So the main thing when we use this decomposition like we have here, I've shown that we have to make sure that the decomposition is actually part of the field. So depending on what field you're using, this may be expensive, this may be cheap. And so for larger fields, basically the same considerations. And if it's possible to have something where you have a cheap decomposition and also an S-box which guarantees that the input leads to a valid output, then you can easily apply that as well. But for different prime fields, we may have to look at it in more detail, yes.
Yeah, I would expect that the bar function would be very cheap with Lasso because you could you wouldn't have to do run checks. You would be able to have decomposition plus operation in potentially 1 or 2 lookups. So it could be very interesting.
Yeah, it's definitely a very interesting topic, and I guess we will look into that as well. Yeah, thank you.
Hi, thanks for the talk. So I wanted to ask the same question, but I've got another question. It's about the affine layer. So we always see in the different designs that we always have the affine layer. That's there normally to do diffusion between the element of the state, if I'm not wrong. But also we see that we start mixing in the S-box the different element of the state. So we already do some diffusion there. Is there any way that we can get rid of the affine layers, or at least, because the affine layer is quite expensive for Plonk, because we've got to do a lot of additions. And I can see that in the different constructions, if I'm not wrong, the cost in Plonk comes from the linear layer most of the time. So have you considered? Yeah,
so we actually considered some parts of that. So there are nonlinear layers. We have a lot of mixing. For example, Feistel networks, LMSC networks, etc. But they come with different problems. And in the beginning, we actually had a design where we didn't have a linear layer. But in the end, it actually led to to a significantly slower design. So we tried to explore that. It's not that easy, and in this case we had to discard it. But maybe someone will come up with a better design without explicit matrix multiplication in the future. But so far we were not that successful in that.
Okay, and there is no problem to use small coefficients in the linear layer?
Yeah, so basically we are mostly relying on the MDS property here, and then the small coefficients do not really matter. But it can matter with different matrices, with different branch numbers, but in this case should not matter at all. Yeah. So AES also has only small coefficients, just for reference.
Okay, we can continue.
Okay, yeah.
All right, so as chair, I take the power to ask the last question. So can you say a little bit, maybe something about the cryptanalysis of these of the hash function in particular? Like we saw that the hash functions are dependent on the field, right? Like how transferable are results that you like find for one field, and then can you move them easily over to others, or is that still?
Yeah, so some properties, for example, in the statistical attacks, you usually rely on the differential characteristics of the nonlinear layers as well as the branching of the linear layers, and there the differential characteristics are definitely field dependent. So for the algebraic attacks, so we are mainly looking for so that these are mostly independent of the field size, but there it of course matters on how many field elements you actually need to instantiate the secure hash function. So in general, the analysis, I would say, can be transferred, but you need to adapt the parameters. For example, as I said, the differential characteristic for the nonlinear layer is field dependent, so you need to plug in the correct field size, and then you should hopefully get a result that is secure in the other field size as well.
Okay, thanks a lot. So yeah, if there are more questions, Roman is around all day,
yes.
So please find him during the breaks, and let's thank him again for the nice talk.
Thank you.